Okay, so one thing that I need to do, unfortunately, in this class, I need to change is we've been starting every class. I said this in dynamics too, so most of you already heard this in dynamics, but I've been starting every class going over questions you have on the assignments, and I can't do that because I have to stop doing that because it's taking too much out of class, and then we'll never cover any new material. So if you have questions on the assignments, you just need to come talk to me in office hours, and I'd be happy to go over them, or email me or something like that, but I'm not going to start class by going through problems anymore.
D2L discussion.
Yeah, I could start a D2L discussion. I know how to do that. It's not hard or anything. It can be tricky with equations and stuff. It's kind of hard to have a discussion about equations, but it can't hurt to open one, so I'll do that. If I remember, which I won't. So I will not do that. Yeah, if you email me, then I will do it. If enough people email me that one of those emails comes in while I'm at my computer that I am able, then I will do it that minute. Yeah, then that'll work, right. Okay, so who remembers what we were talking about last time? No? That's not remembering. That's reading. Strain, right. We were talking about strain. And just like there are two types of stresses, normal stresses and shear stresses, there's two types of strain, normal strain and shear strain. And last time we were talking about normal strain. And remember, normal strains had to do with kind of like a fractional length change, okay? So this time we're going to talk about the shear strains. Okay, so under a general deformation with the assumptions that we're making in this class, a cube of material deforms into what general shape, do you remember? Yep, that's right, parallelepiped. And that means that there are length changes and there are also angle changes. The normal strains gave you the length changes. So now we're talking about the angle changes. So these shear strains produce changes in angle between the faces. So if you start out with a cubic stress element, and each of these is a right angle, under deformation, you get something like this. And I'm going to call this angle theta xy, where theta xy is the angle between the positive x and positive y face. Then the shear strains are represented by the Greek letter gamma. Gamma xy is equal to pi over 2 minus theta xy. Gamma xz is defined as pi over 2 minus theta xz. And gamma yz is pi over 2 minus theta yz. Where, talking about it generally, theta AB is the angle after deformation between the positive A face and the positive B face. And that angle is in radians. So notice that, okay, so think back to normal strains. If you had a positive normal strains are have to do with length changes. If you had a positive normal strain, what was happening to the length? Was the length increasing or decreasing? Increasing, so that's a material that's in tension. If you got a negative, then that's compression. If a shear strain is positive, look at this definition and tell me, so that angle between the two positive faces that are involved, if you have a positive value of this shear strain, is that angle becoming more acute or more obtuse? So a positive value of a shear strain. Some of you are correct. So if this is positive, the angle between the positive faces is more acute. If it's negative, then they get more obtuse. So if it doesn't change angles, then after deformation, that theta is equal to pi over 2, so you get 0 strain. If this angle is less than pi over 2, then pi over 2 minus something less gives you a positive number, and for this to be less than pi over 2, it has to be acute. Okay. Let's do an example. So let's say that we start out with this, where these are all right angles. And say we're using a coordinate system with the x-axis that way and the z-axis this way. And after deformation, we get this angle up here is 1.43 radians. All other, so how do I want to say this? The faces in the planes that aren't shown here. Remain perpendicular. Okay. So what there are three possible shear strains. Which one is going to change? Two of them aren't going to change. Which one is going to change? XZ is going to change, yeah. So XZ is equal to pi over 2 minus, and now you have to be careful on this one. What's the angle that we want to use? So in this case, it's not going to be that 1.43 because that's the angle between the positive x face and the negative z face. So yeah, it's going to be, right, pi minus 1.43, which is, what, 1.57? So this is the angle we want. So that's the angle theta xz. And so that is
1.7.
oh yeah. Right, it has yeah. I was doing it for 3. But let's not approximate pi as 3. That seems a little excessive. Okay, so all right, so pi is equal to 1.43 plus theta xz. So theta xz is equal to pi minus 1.43, which is 1.71. Rad. And so shear strain xz is equal to pi over 2 minus 1.71, which is negative 0.1392. Then for the other two shears, shear xy is equal to pi over 2 minus, that angle stays the same, so that's going to be 0. And yz, same thing, pi over 2 minus the deformed angle, which is still pi over 2, is 0.
So we always start with this cube.
Yeah,
time.
right.
And that's the same as with the stress. It's just like a point, just to represent a point.
Right, it just represents a point, yeah. Just like we had when I was doing the demonstrations with the normal strains, this is way bigger than any reasonable value we're going to get in an actual case. This is way too big for our assumptions. Okay, let's do one more. So this time let's deal with both of these, with the normals and the shear strains at the same time. So let's say that we start out with a cube that's .01 meters, 0.01 meters, and we'll use this coordinate system. And after deformation, we have a height of 0.015 meters, a width of 0.007 meters, and an angle here of 1.3 radians. What are the strains? So start out with the normal strains. The X normal strain is the deformed. Okay, well first let's think through this. So if everything else is, I better write that, everything else is unchanged. All right, so the stuff that you can't see in this picture, the out of plane stuff, the angles don't change, and so if you looked at it from the side, you'd still see right angles, and you wouldn't see any change in length.
It's just this one face.
Just this one face is right.
Okay.
Yep. Okay, so we have a length change in the X direction, a length change in the Y direction, and an angle change between the X and Y faces. So we expect non-zero values for EXX, EYY, and gamma XY. Okay, so let's think about the signs. So in the X direction, does the length increase or decrease? In the X direction, it decreases from 0.01 to 0.007. So do we expect that to be a positive or negative strain? Negative. In the Y direction, it increases. So is that going to be positive or negative normal? So that's going to be positive. And then for the angle change, it gets more acute. That angle between the positive X and Y. So is that going to be positive or negative? Positive. Okay, so EXX is the deformed length minus the undeformed length divided by the initial length. And so you get 0.003 divided by 0.01. This should be negative. And you get a value of negative 0.3. What are the units? That's right, no units. And then the YY strain, that's the deformed is 0.015 minus the initial 0.01 divided by the initial. And so you get a value of 0.005 divided by 0.01, so positive 0.5. And then for the shear strain, you have pi over 2 minus theta xy. Theta xy is the angle between the positive x and y faces, so that's 1.3 in this case. So we got pi over 2 minus 1.3, which is 0.271. All the other values, so that's EYY is non-zero, but EZZ is the same thing as gamma XZ is the same thing as gamma YZ, and those are all equal to 0.
Does gamma have units, radians?
Yeah, radians, but that's kind of no units. Yep.
If you go back to your picture,
Yeah.
we have the height 0.015 meters,
Mm-hmm.
but that doesn't mean that it's the length of the stress.
Yeah, that's a good question. So that's the kind of thing we would have to worry about if we weren't talking about very small deformations. So in this example, that would be an important thing to worry about because we have these really big values. But in our problems where all of our strains are 10 to the minus 4, 10 to the minus 5, 10 to the minus 6, there's no significant difference between whether you're measuring the height or the length. Okay. You see that, how that limit works out as those values get really small?
So technically, do we want to be doing the length?
So technically, I mean, I guess I would say technically we just want to measure the height because if we really wanted to get exact values, there's a lot of other stuff that we're sweeping under the rug that we wouldn't be able to. So for us, this is the value we want, is just the height and then the width. Okay. What about these values? Are these reasonable? No, not reasonable. Too big for our assumptions. Okay. Any questions about that? So the stresses, we had those 6 stress values, and we put them in this cool format called a tensor. That was pretty awesome. Remember that? Man, I felt so cool when I was talking about that. So I'd like to give you something, awesome to put the strains in. But, well, I can give you, it's better than nothing, but it's not a tensor. So how do we organize the strains into a single object? Well, here's the bad news. Strain, the way we're defining it, is not a tensor. For something to be a tensor, you have to be able to use a rotation matrix to express it in different coordinate systems, and we can't do that. So instead, we're going to organize it in a form called the Voigt strain, named after John Voight in Midnight Cowboy. Not really. And so you just organize it into what looks like it's a 6x1 matrix, 6 vertical elements, and it's in this. Okay, so the first 3 are the first 3 are the normal strains, and they're exactly in the order you would expect. So EXX, EYY, EZZ. And then the next three are the shear strains, and those are in the exact opposite order you would expect. So gamma YZ, gamma XZ, gamma XY. So the first three are the normal strains. In a sensible order. The last three are the shear strains in a backwards order. Okay, so from the example above, give the Voigt strain for the previous example. So what we had was that EXX was equal to negative 0.3, EYY is equal to positive 0.5, gamma XY was equal to positive 0.271, and then the other three values were all equal to 0. And so the Voigt strain is negative 0.3 for EXX, positive 0.5 for EYY, 0 for EZZ, and then YZ is 0, XZ is 0, and XY is 0.271. Now, stress is a tensor, but we're going to see that there's a use for representing the stress sometimes in the Voigt notation too. So we'll also sometimes use the Voigt stress. And so the Voigt stress is defined in the same order as the Voigt strain. So sigma sub v, the Voigt stress, is equal to sigma xx, sigma yy, sigma zz, and then sigma yz, sigma xz, and sigma xy. As an aside, you'll also often see the shear stresses written using the Greek letter tau. So then that Voigt stress would be sigma xx, yy, zz, and then tau yz tau xz and tau xy. But nothing changes about those values. It's just a personal preference thing for representing it. So here's the benefit of that Voigt form. For linear elastic materials, linearly, I guess, the stress and strain are related according to the Voigt strain, and I'm going to write out these values. So EXX, whoops, EYY, EZZ. I keep saying E's, but that's because it's easier to say than epsilons. Those are really epsilons. Gamma YZ, gamma XZ, gamma XY are equal to a matrix times the stresses in Voigt form. So sigma XX, sigma YY, sigma ZZ, sigma YZ, sigma XZ, sigma XY. This thing here is, you can think of that as the constant of proportionality for Hooke's law. But what kind of object does that have to be? What size matrix does that have to be if you're right multiplying it by a 6 by 1 and getting out a 6 by 1? Yep, that's right. So this is a 6 by 6 matrix called the compliance matrix. Or equivalently, this is the form we're going to use more often. Equivalently, let the matrix S be the inverse of the matrix C. So this C is the compliance matrix. This S is what we'll call the stiffness matrix. And so talking about it in terms of the stiffness matrix, you get that the stresses are equal to the 6 by 6 stiffness matrix times the strains. xy. Okay, so this is the 6x6 stiffness matrix. So according to these equations, as long as you know the 36 values of the stiffness or compliance matrix, either one, just if you have one and you want the other one, you just take a matrix inverse and your calculator will do that for you. So if you know these 36 values, then knowing the stress is equivalent to knowing the strain. Like you calculate one, then just multiply it by that matrix, and it gives you the other one. And vice versa. Well, coming up with, so say you have a chunk of material and you want to measure those 36 values for that stiffness matrix or for the compliance matrix. That sounds like a major pain, right? Come up with 36 tests that give you these material properties that represent this matrix. Well, it turns out that for our assumptions, we don't need 36 separate values. All of these 36 values can be expressed in terms of two variables. There's only two independent values. So, luckily, for isotropic materials, and that's one of the assumptions that we're making in this class, all 36 values of the compliance matrix depend on just two parameters. Those are E, which is known as Young's modulus, or the modulus of elasticity. And nu, which is called Poisson's ratio. So for an isotropic matrix, for an isotropic material, the compliance matrix is this: 1 over E, negative nu over E, negative nu over E, 0, 0, 0. Then the second row is negative nu over E, 1 over E, negative nu over E, 0, 0, 0. The third row is negative nu over E, negative nu over E, 1 over E, 0, 0, 0. Then the fourth is 0, 0, 0, 2 times the quantity 1 plus nu over E, 0, 0. And then the last two rows, this one term just moves over 1 each time, so 0, 0, 0, 0, 2 times the quantity 1 plus nu over E. And then the last one, that non-zero value is all the way in the 6th spot, 2 times the quantity 1 plus nu over E. And I'll talk next time about the test that you need to do to get that Young's modulus and the Poisson's ratio. But for now, let's just see how this works. So let's see if I have an example here. Bless you. All right, so let's say that we have a steel piece of material or a point in a steel object, and steel has a Young's modulus of 200 times 10 to the 9th pascals and a Poisson's ratio of 0.3. Different mixtures of steel have different values, but they're all in that ballpark. And let's say that the Voigt stress is 5 times 10 to the 7, 0, 0, 0, 2 times 10 to the 7, let's make that one negative, pascals, and then positive 1 times 10 to the 7 pascals. And we want to know what's the Voigt strain. Well, so we just plug these two values into the formula for the compliance matrix, and then multiply this stress tensor times the. I don't know why I thought I was going to sit up here and do that in my head. I'm not doing that. Hell no. But you can imagine. You can imagine what would happen if I did it. You get some numbers. So the numbers generally, so the compliance matrix, something like steel, do you think of steel as very compliant or very stiff? Okay, so the stiffness matrix for steel would have really big values, way bigger than 1, times 10 to the something. The compliance matrix would have very small values, much smaller than 1. And so if we're always going to be seeing stress values that are big and strain values coming out of it that are small. Okay. I ain't doing this. You guys can do it. Okay, any questions about that? I think that's an okay place to stop. Is that? No, let me, no, let's not. 50 minutes is so short. I gotta milk this time. Okay, so how do you calculate E and nu for a given material? You use a mechanical testing machine and you take a little strip of whatever material you're testing, and you have obviously very strong calipers holding it on each end. So this is called a tensile test. And as you apply a tensile force, you divide F by the cross-sectional area to get, we'll call this the X normal stress. So let's think of a coordinate system like this, with the x-axis along the long axis of that sample piece. This area is the cross-sectional area before deformation. And then you measure the length change in this piece as you stretch it. And the Young's modulus, E, then is equal to that measured XX stress divided by the measured XX strain. So what are the units for Young's modulus? Well, this is pascals, this is unitless, and so you get units of pascals for Young's modulus. For structural metals, it's somewhere between 100 and 200 gigapascals, so 100 to 200 times 10 to the 9th pascals. And then to measure the Poisson's ratio, during that tensile test, you measure, so you're measuring the length change, and you're also measuring the width change or the thickness change. And in general, like if you pull on a material in one direction, it's going to contract in the other direction. And if you push on it in one direction, it's going to bulge out in the other direction. And these are, so we're still using this coordinate system. Then the Poisson's ratio is the negative of the measured, I'll call it the YY strain, but it could also be the Z strain, would be normal strain, would work too, divided by the loaded normal strain. So this is the normal strain along the loading axis. And this is a normal strain along a non-loaded axis. The SI units for Poisson's ratio. Well, you can see you have a strain divided by a strain, and so this is unitless. And to make sense out of what the Poisson's ratio is, it measures how much off-axis contraction you get for a given axial stretch. Let me put one more thing in here. A material that's incompressible has no volume change when it's stretched or compressed. No volume change under deformation. And in that case, Poisson's ratio is 0.5. For most metals, it's somewhere close to 0.3. So you get a little bit of when you stretch something, you get a little bit of increase in volume. But the increase in volume you would get from the stretch is offset a little bit by contraction along the other axis. Any questions about that?
So is 0.5 the greatest?
Yes, it can't be any bigger, right? You never have anything bigger than 0.5. Any other questions? Okay, that's it.
Can you go back to the big 6x6 matrix?
Yeah, let me